Hello, everybody. Today we're going to be looking at error in measurements. The reason being, anytime you take a measurement, anytime you collect data in order to study a physical phenomenon, there's always a degree of uncertainty or error involved in that measured value. And that error can come from different things, not necessarily just what you do in the act of measuring, but it can be the measuring device itself, the situation in which you're measuring. So we're going to be looking at error in our measurements. Now, there are three types of error, and you've heard of them before, although you may have two of them especially, you may get confused from time to time. And so we're going to try to take care of that little problem today. The first type of error that we're going to be looking at is accuracy. Accuracy, okay? Now, accuracy is when you compare a measured value to an accepted value. Okay, so a good example to use or analogy to use for this is a target. Suppose you're going to shoot arrows at a target off at a distance. Now, where accuracy is concerned, the accepted value for this analogy would be the bullseye. The bullseye is the accepted place to hit with your arrow to make yourself accurate. Okay, the further away from the bullseye you are, the less accurate you are. So let's look at an example where we might have some measurements that look something like this. Okay, now, is this person accurate? Well, fairly accurate. At least 50% of the shots are on or near the bullseye. The other 50% may be away from the bullseye, but they're on different sides of the bullseye, so that if you looked at the average of those four, they'd be near the bullseye also. So you could say that person is fairly accurate. Okay? Now, when it comes to measurement, that means you have to take your measurements and compare to an accepted value. A classic example of an accepted value for a measurement is the acceleration due to gravity. Okay? Now, it is an acceleration. Little g does not stand for gravity. I think it's a poor choice that they used little g to represent it because it gives people the idea that that is gravity. It's not. It's the acceleration, the rate of change in velocity that gravity produces for a falling body. Okay? And the accepted value for that is 9.80 meters per second squared, or 9.80 meters per second change in velocity each second. So that is the accepted value, or if you will, the standard by which we compare all other measures of acceleration due to gravity. Okay? Now, let's suppose that you're in a lab and you want to take a measurement of the acceleration due to gravity. And let's suppose you come up with some measures. Let's call this measurement number 1. And let's say it has a value of 9.91 meters per second squared. And then you do the procedure again and you come up with a second measure of value 9.65 meters per second squared. And you want to look at your accuracy in measuring. Well, you would have to take each one of those and compare it to the standard, okay? And we're going to learn how to do that right now. In fact, there are two ways that you could look at the accuracy of these measurements. Here they are right over here. The accuracy of measurements. All right, one way to find the accuracy of measurements is absolute error. Now, you've actually heard of absolute error before. you just called it by a different name. If you had Miss Miller or Miss Elswick for chemistry, then you know absolute error is simply a difference between the accepted value and the measurement. Look what it says, absolute value difference between the measured value and the accepted value. Now, what does absolute value difference mean? It means once you take the difference, you drop any minus signs, because we don't care if the measured value is greater or less than the accepted value. We just care how far it is from it. So you're going to take the measurement minus the accepted value and absolute value signs so that you always have a positive answer. Okay? So this is the definition for absolute error. Oops, there. Okay. In fact, for our measurements, let's take the first one. If we find the absolute error of measurement 1, now look at the subscripts I'm using. In physics, we use subscripts to help us identify or distinguish between different items that use similar variables. So, for example, we could find the absolute error of measurement 1 right here, and we could also find the absolute error of measurement 2. Since both are absolute error, we use the number subscripts to indicate which one is which. Okay. Now, in order to do this, we would take the first measurement, 9.91. We would subtract the accepted value. And as you can see, if you subtract, you're going to get 0.11 meter per second squared difference between the two. Okay? And if you want, you can go ahead and do it with the second, but I think that's probably fairly clear example right there. Now, that's not the only way, and let's look at the other way of looking at the accuracy of our two measurements. This one takes a little bit further. It goes a little bit further than this. We call it relative error. And a few minutes ago, I was saying that you knew it by another name. I didn't mean this one. I meant this one, but I wasn't thinking straight, so there you go. Okay, so relative error is what you know from Miss Miller and Miss Elswick as percent error. So percent error, if you want to put a percent right there, you can, but it's still relative error, R-E, okay? And it is basically the absolute error divided by the accepted value times 100. Or if you will, if we substitute, we get the measurement minus the accepted divided by the accepted times 100. So this right here is what we use for relative error or percent error, as you remember it being called. So let's go back to this one right here, because we already have the absolute error for the top part. So for the relative error for measurement 1, we would say the absolute error that we found a moment ago divided by the accepted value times 100. All right, so that would give us 0.11 meter per second squared divided by 9.80 meters per second squared. And notice what happens to the units here. The units cancel from top to bottom because we're supposed to end up with a percent. Percentages don't have units. So the relative or percent error here is going to be a value of, well, basically 1%. Okay? If you stick that in your calculator, you should get 1%. All right, so these are both two ways of looking at the accuracy of measurements, but you're always comparing to the standard, to the accepted value, okay? Now, that's what makes it different from the other type of error that we'll be looking at in a moment. Now, we've been looking at the accuracy of the measurements themselves, the numbers that you write down, but what about the measuring device? Okay, well, when you want to talk about the accuracy of the measuring device, you got a little problem. Remember, you're always comparing to a standard with accuracy. And when it comes to measuring devices, well, where are the standards? Oh dear, they're kept over in France at the International Bureau of Weights and Measures. So how well can we talk about the accuracy of our measuring devices? Well, we'd actually have to take them, pack them up, put them on a plane, go to France, get them off, go to the International Bureau of Weights and Measures, and compare those devices to the standards. In other words, you'd take your triple beam balance to the International Bureau of Weights and Measures. You'd get their standard for 1 kilogram, sit it on the balance. If the balance does not say 1.00000 kilograms, then it's not very accurate, is it? If it says 1.0100, you've got some error involved in your measuring device. Well, yes, we could do that, but it'd be very expensive. So in this class, we don't really look too much at the accuracy of the measuring device. We simply assume that for our purposes at the high school level, that they are accurate enough. All right, so we've looked at the accuracy of the measurements themselves, and we've looked at the accuracy of the measuring devices. Now, let's talk about the second form of error, and this is the one that a lot of people get confused with the first, and they want to try to interchange the words, even though you really can't because of their definitions. Now, where accuracy compares measurements to an accepted value, precision is very different. It is a comparison also, but what it compares to is different. Precision is comparing 2 or more measurements to each other, not to an accepted value. So in our analogy for a target, let's suppose that we had one person that shoots their arrows and ends up with something that looks like this. Okay? Now, we would say that person is imprecise. In other words, they don't have a lot of precision, because look at their shots. They're all over the place. In fact, these two are the only two that are near each other at all. So this person is fairly imprecise. Now, what about this person right here? Okay, now that person may not be accurate because they're not near the bullseye, but they are precise. In other words, they're consistently measuring or shooting the same location over and over. So this person would be considered precise. Okay? All right. Now, let's take a look at the next page, which allows us to find the precision of the measurements. Where is it? There it is. Okay, the precision of the measurements. When we look at the precision of measurements, there's 2 ways we can do it. Neither of them is very difficult, although for one of them you do have to do something. You have to do one calculation before you can do the main calculation, but that's okay. It's no big deal. The first one is called deviation. Now, this is a term you've heard before in general, deviation, but it's basically defined as the absolute value difference. There's absolute value again. That means we're going to get all positive answers, because if they are negative, we're going to drop the minus sign. We don't care if our values, if one value is greater than another or less than, which is how you would end up with a negative sign. So we're just going to take the absolute value difference, that means subtract, between any single measure and the average of all the measures. So here's what it would look like. Deviation is a single measure n, where n could be measurement number 1, number 2, number 3, or so on, minus the average of all the measures that you took. So if you have 5 measurements, before you can find the precision of measurement number 1, you have to find the average of all the measurements first. Then take each individual measure, subtract the average from it, and you get that measurement's deviation. Okay? Now, the next thing. The last one here is something you may be also familiar with from chemistry. This is percent difference. Now, since it is a percent, that means no units. Deviation, there would be units because all you're doing is subtracting one value from the other. You're not dividing, so the units cannot cancel out. So percent difference, you will be dividing. That means the units will cancel out and you'll end up with a percentage. So let's see what percent difference is. Percent difference is when you're going to compare two measurements only. Okay, only two of the measurements that you took. And I'll explain which two we normally use in a few minutes. But it's called the percentage that the difference between the two measurements is of the average of the two measurements. Oh, now that sounds complicated, but it's really not. Let's just take it carefully. Okay, and we do actually use absolute values on the top, although it doesn't say it, but we're going to. All right, so it's a percentage. You're going to need it times 100. That the difference between the two measures. So you've got measurement 2 minus measurement 1. It's a difference between the two measures that you're looking at. And then you're going to divide by the average of the two measures. In other words, the midpoint of the two measures. So that would be 1/2 their sum. That would average them, wouldn't it? If you add two things together and divide by 2, you get their midpoint, or in this case, their average. So this is how we're going to find percent difference between two measures. But how do we know which two measures to look at? Well, often the percent difference is used for the most and least precise values. In order to see a range of error. So you take your measurement that was the most precise and you take your measurement that was the least precise according to deviation, and you would find the percent difference between them, and that would give you your range of precision, okay? Everything would fall within that. If your most and least precise measurement are 10% difference, then that tells you that the other measurements were less percent difference, had a less percent difference than even those. So that's good to see what your range is for your percent difference by using your most and least precise to compare. Okay, now the third source of error, and this is where you come in when you're actually taking the measurements. Okay. Oh, wait, no, I think I forgot something. I'm trying to start this and I got to talk about this, don't I? All right, well, if you remember, right here, we talked about the accuracy of the measurement, the number that you wrote down, and we talked about the accuracy of the device you got it from. Now we're going to do the same thing with precision. We've already talked about the precision of the measurement you wrote down. Now let's talk about the precision of the device you got the numbers from, because that's where measurements come from. They come from the measuring device. So let's take a look. It says here that the precision of the measuring device is defined by, and you can underline this, box it, it's the smallest division physically marked on the device, okay? The smallest division actually marked. It may not even have any numbers associated with it on the device, but it's there, okay? Let me give you an idea. All right, here we go. Here is, if I flip this over real quick, here's a measuring device. It's just an ordinary ruler. Now on this top part, I have the inches. And if you'll notice, the whole inch marks, which are the biggest ones, those are marked but the half-inch marks are not marked, and neither are the smaller ones. So if you wanted to see what the precision of this is, you would have to see what are the smallest increments physically marked with a hash mark on here. Well, that would be these little marks right here. Okay? And those, if you break it down, would be 1/16 of an inch, because here you have two halves, and then you have 1, 2, 3, 4 quarters, okay? And each quarter is split into two bigger areas, which would be an eighth, and then 4 smaller areas, which would be 1/16. Okay? So the precision of this inch ruler is 1/16 inch. Okay? But what if we flip it over and look at the metric side? It's a little bit different. Now remember, centimeters are smaller than inches. So that's how you can see the difference between the inch side and the centimeter side. Now in labs, we never use inches. We only use metric in labs, okay? So here we have whole inches from one big line to the next big line. We also have half inches in between each one. But then there are these teensy-weensy little places, little divisions marked, and there are no further smaller ones. So what would these little teensy-eensy ones be? Well, if you'll count them, you'll see that between the 9 and the 10, there are 10 divisions. There's 10 spaces, and each one would be 0.1 for a 1/10 centimeter. But since there are 10 millimeters in 1 centimeter, it would also correspond to 1 millimeter. So the precision of the centimeter side would be either, you can state it either way, it's still correct, and I accept it either way. You could say 0.1 centimeter or 1 millimeter because they are the same thing, okay? So that's how we do that. We actually look at the smallest division marked. Now, there are other measurements. Suppose we go back to the inches for a minute. I want to show you, not all inches have the same precision. Look at this one. These are also inches, the black ones. But in this case, the inches are divided up into tenths, not eighths or 1/16 or quarters. All right, these are actually divided up into tenths. So the precision of this ruler would be 1/10 inch. Now look at this one. This one's even more different. Okay, although it is a little more like this bottom one. But look at the inches now. We've got 1, 2, 3, 4 smaller divisions in the inch division. So that means each one of these is a quarter or 0.25 inches. Okay, so 3 inch measures, but each one has a different precision. We have a 1/16, a 1/10, and a 1/4 inch. How about that? Okay, so all devices, you can determine the precision by simply looking at the smallest division marked. Let's look at a different type of device really quickly. Hang on, I'm trying to get my stuff out of the box. Okay, now you guys know what this is. This is a protractor. Ooh, I'm going to need some more light. Can you give me your flashlight? Yeah, my dining room light apparently is not quite strong enough for this. So let's just shine some light on the subject here. Ah, there we go. How about that? Okay. So now, if you look, you guys know that a protractor measures degrees of arc. And in this case, if we look at the degrees of arc, and I'm going to go between 110 and 120 right here. I'm sorry for my shaking. Those are my tremors. Each of these, from 110 to 120, it's divided up into 10 small spaces. So that means each one of these is 1 degree, because to go from 110 to 120 in 10 spaces, each one would have to be 1 single degree. So the precision of this protractor is 1 degree. Now, look at this next one. Now, this one's going to be a little tougher to see, and I think I'm going to have to try to focus in a little bit more on it. Okay, if you can see from 110 to 120 now, you not only have those 10 regular spaces for degrees, but each of those degree spaces is now divided into 2 divisions. So those are half degrees. So on this protractor, from 110 to 120, there's 20 spaces. Each one is half a degree. So the precision of this protractor is 0.5 degrees. Different from the other one, isn't it? Okay, so all measuring devices have a precision, and it's simply defined by the smallest division physically marked on the device, the smallest space, and you simply have to figure out what fraction that would be. All right, now, I want to get through the next part fairly quickly. So here we go. This is the third type of error that you can have. And again, like I said before, this comes from you yourself. You're measuring on the measuring device. And yes, I hate to say it, we're talking about significant figures or digits. Significant figures or digits. Now, very important to understand. The definition of significant figures is all the digits in a measure that are known for certain plus, that means there's something else too. The first uncertain digit, or your guesstimate of where an object or an arrow falls between one mark and another mark, okay, when there are no smaller marks. So all the digits in a measure known for certain plus the first uncertain digit. That is the definition of significant figures. Now, where do significant figures come from? Well, right here on the device. Significant figures come from the device itself, and you are the one who reads them off and writes them down. So real quickly, we're going to look at 2 different rulers and how to correctly read according to their precisions. So we're going to use a standard centimeter ruler where these big numbers right here are the centimeters. And same over here. I'm going to go with 5, 6, 7, and 8 though, just for fun. Okay? Now, what we're going to do is we are going to find the length of a paper clip. Oh, looky here. All right, there's a paper clip. So what we need to do, and here's the way you normally do it, unless you line up the end of the paper clip with the 0 mark, and watch out for that. On some devices, the 0 mark might not be quite stamped on the end, so it's not always a good idea to line it up with the 0 mark unless it's very clearly visible, okay? So in this case, because I have no 0, I'm starting at 1, I am going to take a reading on the left side, a reading on the right side, and then I'm going to subtract the 2 to get the length. So how do we do this properly? According to the precision and get the right number of sig figs? Watch this. All right, starting from the end of the ruler, going to the first arrow. We've got 1 whole centimeter for certain. So I'm going to put a 1, and now we got fractions. So I'm going to put a decimal. Now, between the 1.0 and the arrow, how many whole millimeters do we see for certain? Well, 1, 2, 3, 4, but not another one because it looks like the arrow is somewhere between the 4th, somewhere in the 5th millimeter. So we can only say for certain 4 whole millimeters. Now, between the 4th and the 5th, here's what we can do. We can say it's either right on the 4 and say put a 0, or we can say it's closer to halfway between and put a 5. So we're going, as you can see, that looks like it's right halfway between. So I'm going to put a 5 there, and now it's 1.45, okay? And that would be centimeters. Now, on the right side, we do the same. We go from the end of the ruler to this arrow. How many whole centimeters do we have? We've got 1, 2, 3. Okay, so we put a 3 down. Now we're going to go to fractions. Between 3 and 0 millimeters and the arrow, how many whole millimeters do we have for certain? Well, we don't have a whole one, so we put a 0 for the whole millimeters past the 3. Where between the 3 and the 1 millimeter mark is that arrow? Well, here's our guesstimate. We can either say it's 3.00 right on the 3 mark, or we can say 3.05, that it's halfway to 3.1, and I'm going to say halfway. All right, now to get the measurement, all we have to do is subtract, and if we say 3 minus 1.4, I think you see it's 1.6, but now wait a minute, we measured 2 decimal places. Yes, it was estimated, but we measured it. So we have to put 5 minus 5 is 0. We got to have 2 decimal places there as well. So there's the length of our paper clip. Okay? Now, look, this one has less precision. How is that going to change our measurements? All right, so let's say that we have a pencil. All right. Let's say that we have a pencil, and we're going to measure the length of it. So we start with the left arrow, and from the end of the ruler to that arrow, we can see that we have 5 whole centimeters. It doesn't go to 6, so we can say 5 point. Now we need our fractions. Okay, now look here. We can go 5.5. Oh, look. 5.5. And then we can guess how much further, let's see, how many whole millimeters do we have for certain? 5. Okay? And past that, how would we guess? What would you guess for the millimeters? Is it 5 or is it 3 or 4 or 2? I'm going to say 3. This one's a little different, isn't it? Because you got to guess a little differently on that one. On the right side, we'd go from the end of the ruler to the 8. And to me, it doesn't look like it's a half or a whole. It looks like it's right on there, so we're going to say 8.0. And you know what, guys? I think I did that one. Let's see, 5. Oh, here's what we have to do on this one. I kept thinking that's not supposed to be 2 decimal places. Okay, so what we have to do on that first one, we have to say it's 5 point, well, it goes past the 5.5, and we can estimate, maybe 6 or maybe 7. So 5.7, there we go. That's better. All right, so when you have less